Hey guys, I hope you're doing well. I just wanted to kind of talk about at least the lab for that we're going to be having today. So this is lab 5. And I'll just kind of do this for most of the time where I will come in and I'll talk to you about the lab, specifically kind of things you want to know, at least where we're going forward, and kind of the general ideas for what I might be wanting to get at for some of these questions going forward. So this lab is mainly going to be covering the ideas of partial derivatives, contour plots, basically chapter 14. So contour plots, partial derivatives going forward, and also the idea of tangent planes, that 14.4 that you guys just learned on Wednesday. So at least when we're going through these labs here, they've been somewhat modified. So I'm just going to kind of take you through a little bit of interesting things. The first part here is all about contour plots. So again, the idea of contour plots are that basically I'm taking the height of a function. I have a function f of xy. It talks about the height of a function. Let's say this function right here, 1 over 1 plus x squared plus y squared. And I'm basically taking slices of it with just z equals k, right? And I'm taking slices of them and seeing what projection happens on them. What are the intersections between the slice? Kind of, you can imagine if I have some like anti-particle wipes, I'm taking slices of this at every single height and seeing where the contours are, right? Where am I always at a height of 10 or 20 or 30 or 40 or negative 10 or negative 20 or something like that? And in this, you actually use the function contour plot if I want to get what the contour plots are. There's a couple of cool options that you can have. Contours is one of them. It tells you how many contours you would like to plot on your domain. On top of this too, what we're going to be able to talk about here is the idea of limits as well. So in this problem, make sure exercise 1, make sure you kind of just go through and if you have to write comments here, make sure you write them in text. If you're having trouble with that, go to command 7, something like that. Also make sure you use the limit command. I've showed you how to use the limit command here to check your answer for part B and go from there, and making sure you have the contour plot too. Now for exercise 2, I know this looks like a really long problem, but it's actually not too long. It's actually got a really cool animation that I've kind of made for you guys. So the goal here again for this exercise, making sure that we're trying to understand the difference between two different plots and how we can show the distinction between them using contours, even though they have pretty similar contours and level curves. So this code, I'm just going to ask you basically to copy this code. Now, if you have some issues with copying this code, make sure that all of these different things are on the same lines when you copy them in to your code specifically. You might get some that you might have like plot G here comes up to here. Make sure you just enter them and make sure they're all in one block. You should get some manipulate functions. Again, the manipulate function where you can be able to move the slider and kind of see what happens there. So play with it and hopefully it's a cool little animation to kind of show you what's happening. And make sure you comment on your findings a lot of times. The more specific you are, the better. And if you're having trouble figuring out the comments, definitely talk to me or ask other people. It's always a good thing to do that. Exercise 3, not too bad. Make sure you just do this by hand. Exercise 3, compute this by hand. You can just explain it, and you can just write it down very nicely how you do it, why you find the domain in such a way. And then use the function domain. You might have to go on Mathematica's website to figure out how to do this. It's not too bad at all to do this. Just make sure you use the function domain to find that. Partial derivatives are kind of interesting in Mathematica. It's not with the prime notation anymore. We are allowed to be a little bit more specific. So for instance, if I have this function, h of xy, and I want to compute the partial derivative with respect to x, how fast am I moving in the x direction? How fast is the height changing? What I do is I actually have to use this d command here. This capital D. This capital D here, I then plug in my function h of xy, and if I want to take the derivative with respect to x, I plug in x. And similarly, you should kind of see, if I plug this in, I'm just going to show you something very quickly. If I actually show you how to do this in Mathematica, it's actually pretty interesting. So if I show you here, so if I plug in just a random function, just, d of, oh no, actually, let me just type in h of xy. I'm just going to make something up, x times y, really quickly. Now, what's cool is, it actually, I don't know if you guys can see it, But the x right now, because I've said I want to take the partial derivative with respect to x, the x here is actually in green, and the y is in blue. And what is that actually saying, right? Mathematica is saying here, okay, I want to keep y constant. Right? I'm making y a constant. That's why it's actually blue. That's kind of what Mathematica says. If it's blue, it's a constant. And similarly, if I change this to a y, to make the derivative with respect to y, I make x a constant now. So Mathematica does some really nice things like that. And if I wanted to evaluate something, I can calculate that. But if I wanted to evaluate this at a specific point, you can actually use this command. This is kind of a replace all command. And what we do is I say, okay, let's say I want to go x to 4 and y to 1, something like that. And I would get 4. I would get an output. It would plug in the numbers x equal to 4 and y equal to 1 from there. And so it's kind of nice. And we can also kind of extend this to going forward and making double derivatives. So for instance, if I want to take a second derivative with respect to x or with respect to y, or even my mixed partial derivatives, I'm going to take a double derivative. So for instance, here, I would go the derivative. Let's say I want to do 2 derivatives with respect to x. I would take the derivative of h of xy with respect to x, and then I want to take the derivative of that with respect to x. Here. This is not really too complicated of a function, so if I was to make this a little bit more complicated, this would be a little bit better. Something like that. If I want to take a mixed partial derivative, maybe with respect to x and then with respect to y, I would have changed these orders, right? If I want to take it with x and then with respect to y, kind of go like that. And again, if I want to evaluate things, I can also do that too. I would get something like that. So this is kind of the ideas of derivatives. It's not too bad, thankfully. And then that's the last couple of things I wanted to share with you. I know I'm not going to take too much of your time here, but I just want to at least kind of go over kind of what we're going to see here. And just make sure here, if you're having trouble with this problem of kind of which graph corresponds to which, again, remember what the idea of partial derivatives are. If I'm taking the partial derivative with respect to x, it's saying how fast is the function height changing as I move in the positive x direction, and same thing with the y there too. And make sure you follow the lack of colons here once in part D. It's an important thing to remember. And make sure you comment on, will these always be true, the second partial derivatives. Make sure you kind of highlight something important. And lastly here, the linear approximations. So the linear approximations here, what we're going to be showing you, definitely try to do this first part here. Definitely go through it and make sure you understand what's happening. We're going to define our function, right? We define our function that we're taking the linear approximation of. I'm taking it at a specific point. And again, we have this nice little plane, right? This is going to be a linear approximation. It's going to be a plane on top of my surface, just like that. And so doing this, we can again evaluate fx and fy, making sure you apply the correct, finding the derivative with respect to x and respect to y at the exact point that we're trying to find the tangent approximation to. And then we plot it. So we can actually see here specifically that we're going to get a plot and we're going to get something that's attached to it, like very, very close, that tangent plane. And this plot right here, again, we again have this very long, it looks like a long problem. It's not too long, I promise. It looks just like there's like a huge block of code that you just have to copy and paste. Make sure again that each one of these is on a different line. Important to do so. Important that you do that. And then make sure you use the manipulate command down here again and just copy and paste this into another cell block too. This will then allow you, this A is changing the domain size. So we're getting closer and closer and closer to my point rather than we're shrinking that domain. And just make sure you write the comments down and then save it. Again, this is due Saturday night. So if you have any questions, ask me or yeah, anything else you want. So I hope you guys are doing well. And yeah, I'll talk to you soon.